This is bonding video number 6. By the end of the video, you should be able to determine if you have a covalent bond that is polar or nonpolar. To do this, you're going to need your bonding video number 6 worksheet, also available on Edline, your electronegativity table, which looks like this. It is found in your bonding packet and is also on Edline, as well as a pencil, because you will be turning in your bonding video worksheet tomorrow. Now, we've already started working with electronegativity differences, and we said that anything above a 1.7 is ionic, and anything below this range was covalent. The reality is, this is a continuum, or a spectrum between the two. At this point, you are 50% ionic and 50% covalent. So at this point, the 1.7, you start to act more like ionic and a little bit less like covalent. But in order to have a tiebreaker, we say 1.7 and higher is ionic and anything less than covalent. So to recap that, the type of bonds you have is a range or a continuum. As you go up, you become increasingly ionic, to the point that at 1.7 and higher, you're called ionic. When you go down, you become increasingly covalent. You get more covalent characteristics. Below 1.70 or 1.69 and less is covalent. Now we're going to have some additional distinctions here. Since as you go down, you become increasingly covalent and you're sharing your electrons extremely well, everything down below the 0.40 part is considered a nonpolar covalent bond. So in here, anything from 0 up to and including 0.40 is considered nonpolar covalent. This is when your electrons are shared perfectly. Because remember, covalent is about sharing, and ionic is about transferring electrons. Now in this region in here, you're starting to share, but not sharing as well as you used to. This is considered a polar covalent bond. Your electrons are being shared, but they're not being shared equally. So from 0.41 up through 1.69, you are sharing them, but you're not sharing them perfectly. The electrons will be more with one atom or the other. Let's do some examples with this. Starting with our first one, barium oxide. If we take a look on our periodic table, we can see what the charges are for barium and for oxygen. So oxygen's 3.5, barium is 0.9. So 3.5 minus 0.9, we get a difference of 2.6. This means that barium oxide is going to be ionic. Let's try another one. Hydrogen bonded with hydrogen. Hydrogen is 2.1. 2.1 minus 2.1 is 0. This is going to be a nonpolar covalent bond. So it's down here. Nonpolar covalent. Let's try another one. Carbon and hydrogen. Now yes, I have multiple bonds, but I want to look at one of these bonds. Carbon from our table is 2.5 minus 2.1 for hydrogen. We get a 0.4 difference. This is just on the nonpolar region. So this is also going to be a nonpolar bond. So down here, we have the nonpolar covalent bonds. Over here, we have the ionic. But between these two, the hydrogen-hydrogen is a little bit more nonpolar than the carbon-hydrogen one is. Let's look at our last one, water. Once again, we want to look at one bond. So we have the 3.5 for the oxygen minus 2.1 for the hydrogen, 1.4 difference. This fits right in the middle. This is going to give me a bond that is polar covalent. They are sharing, but they're not sharing perfectly. In this case, oxygen, because he had a 3.5 electronegativity, and hydrogen with only a 2.1, the electrons are going to be over here more than they are over here. The electrons are being shared, but they're going in that direction. Dipole. Anytime you have equal but opposite charges that are separated by a short distance, it is called a dipole. Specifically, we've been talking about bond dipoles. Bond dipoles, same kind of definition, are going to have an equal but opposite charge separated by a short distance in a bond. The resulting bond is going to be called that polar covalent bond that we just saw. This is where we have a difference in electronegativity from 0.41 up through 1.69. They're sharing, but they're not perfect. Taking a look at our water molecule, let's show what the bond dipole looks like. If you had a bond between hydrogen and oxygen, see our bond, the electrons are going from the hydrogen to the oxygen. So that when you're done, oxygen is slightly negative and hydrogen is slightly positive. Now this symbol right here is, like on the Greek alphabet, it means slightly negative. It's not a full negative charge, it's a slightly one. If it was a full negative charge, it would be an ionic bond. And this side is slightly positive. The side that has greater electronegativity is going to pull the electrons towards it and make it a little bit negative. This is how we show the bond dipole. We draw the arrow in the direction where the electrons go. We put a little plus sign on the far end to show that this side is going to be slightly negative when it's done. So the electrons are going that way.